Oh, look at Mr. Happy. He's so happy. He's remembering C2 and when maths was easy. And the hardest question you got was, what's the equation of the tangent to the circle? And then he's chuckling to himself because he remembers a time when he thought that to get the gradient, because he knew it was like mx minus a is y minus b, and then he thought, to get the m you have to differentiate, and then he did this, 2x plus 2y equals 0, thinking that you could just differentiate everything with respect to x like this, which of course you can, but when you differentiate x squared with respect to x, you get 2x, and when you differentiate 4 with respect to x, you get 0. But when you differentiate y squared, not with respect to y, if you differentiate it with respect to y, that's 2y, that's fine. But then if we try and differentiate with respect to x, we're not going to get y squared. In fact, what are we going to get? We just don't know. And that was the whole point, was that when people try to do that at C2, you have to point that out and say, no, we can't do this. You can't differentiate that. You're going to have to use the fact that the tangent is perpendicular to the radius, and then find the centre of the radius, and then find the gradient, and then do negative reciprocal, and then everybody's happy. So you're not in C2 anymore. You're in C4. And let's have a look at how we actually would go ahead and differentiate this, because surely it's possible. Surely it's not that difficult to differentiate x squared plus y squared equals 4. So the only bit of this that's difficult is differentiating y squared with respect to x. But look, it's just the chain rule. So the mother function is the squared, and the inside, the baby, is the y. So let's just go ahead and differentiate the mother and leave the baby inside, like that. And then we have to differentiate the baby. Now, you might be thinking, this is really hard. How am I supposed to differentiate the baby, right? The baby is, here he is. Oh, that's a brilliant baby. Equals y. The baby is y. So how are we supposed to differentiate y with respect to x when we don't know what y is? It's not like I'm doing d by dx of like 3x plus 1 squared, and then I could do two lots of, there's the mother function with the baby still inside, and then we differentiate by the derivative, that we multiply by the derivative of the baby, which is 3. But this here is the derivative with respect to x of the baby. And in our case, the baby is y. So what we're going to put on the end here, what we're going to multiply by, is dy by dx, which is just the derivative of the baby, y, with respect to x. So actually, this one, C4, is easier than this one, which is C3, because in C3, you actually know what the baby function is, so you have to actually differentiate it. Whereas in C4, implicit differentiation, you don't know what the baby is, so you can't actually differentiate it. You just write down that you would be multiplying by its derivative. That's all. So it's just the chain rule. You don't even need to learn anything new. Okay, let's have another go at the equation of this tangent in a C4 way rather than a C2 way. So let's see if we can solve this in a C4 way rather than in a C2 way. So we know that the equation of the tangent is mx minus a is y minus b, because all lines have that form. And we know that the point we're interested in is the point 1, root 3. X is 1, y is root 3. This is our problem, m, and this is what we couldn't do at C2, but we can do now. So let's take our original equation and differentiate everything with respect to x. So we get 2x plus, now we need the chain rule, we differentiate the mother function, which is squared, giving us 2y, and then we multiply by the derivative of the baby, which is a y. And then we get 0 on the right hand side. We can move the minus 2x over to the other side, and then we can divide both sides by 2y, giving us dy by dx. That is your first derivative obtained by implicit differentiation. And we can cancel the 2's. Now, instead of like in C1 where you sub in x to see what the gradient is at a certain point, we need to sub in both coordinates now, 1 and root 3. So dy by dx at the point 1, root 3 is minus 1 over root 3, and that's that gradient that we needed for the equation of the tangent. So the actual tangent is minus 1 over root 3, x minus 1 is y minus root 3. Okay, look at this lovely one. This is going to be fun. So an implicit function is one, well, it's easier to say what an explicit function is really. An explicit function is a function which has been written y equals, so you're explicitly linking your y coordinate to some function of x. So you're saying, I know what x is, and I can explicitly now work out what y is. An implicit relationship between x and y is where you have them all jumbled up together. So they are linked. If I told you x, you could find y, for example, the equation of a circle. If I told you x, you could find y. If I told you y, you could find x. But you'd have to do some manipulation. Whereas with an explicit function, if I tell you x, you can just put it in, and then no manipulation needed, you can find y. So this is a really nice example of an implicit relationship between x and y, and it's a beautiful heart shape. And so you can get much better graphs using implicit relationships. So let's see if we can come up with the equation of this line here. This is the tangent at the point 1, 1. So it's going to be m, x minus a is y minus b. And we know that this is 1, the x-coordinate, and the y-coordinate is also 1, just because I can see from the picture. And now I need the gradient, so I'm going to differentiate. Okay, I've got a big mother function here, cubic. So I'm going to differentiate the mother function first, leaving the baby inside, and then multiply by the derivative of that baby. So the baby is x squared plus y squared minus 1. Let's differentiate the x squared. Now let's differentiate the y squared. Well, that's a mother in its own right. So differentiate the mother function squared, multiplied by the derivative of the baby. The baby is a y. And 1 differentiates to 0. Minus, oh, this is exciting. We've got a product. So let's hold still the y cubed and differentiate the x squared, giving us 2x. Then let's write plus, and let's differentiate, let's hold still the x squared and differentiate the y cubed. That's again a mother function, chain rule. So we need to differentiate that mother function, cubic, and then multiply by the derivative of the baby, which is a y in this case, and then the derivative of 0 is 0. See, wasn't that bad? Right, now I want this to say dy by dx equals. I think that's going to be a bit of an enormous job. So rather than rearranging to make it say dy by dx equals blah 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 and then subbing in x is 1 and y is 1, I think I might just sub in x is 1 and y is 1 as it is, and then rearrange to see what dy by dx is. Let's try that. So if x is 1 and y is 1, then what do we get? 3, lots of 1 plus 1 minus 1 times 2 plus 2 of the gradient minus big bracket 2 times 1 plus 3 times 1 times 1 times dy by dx is 0. Okay, let's give myself a bit of room here. Key. You could be pausing the video, by the way, and having a go yourself. It is fun. Right, how are we doing? 1 plus 1 minus 1 is 1. 3 times 2 isn't 3. It's 6. 6 plus 6 dy by dx minus 2 minus 3 dy by dx equals 0. Okay, how many dy by dx have I got? 3 dy by dx, and I've got 4 minus that equals 0. So dy by dx, the gradient at the point I'm interested in, is 4/3. So that goes in my gradient function. Where is it? Hang on, I was trying to move that out of the way. So here's my gradient function at the top, and I've now got the gradient as well, 4/3. So that line, that blue line, the equation of the tangent to the heart at the point 1, 1, is 4/3 x minus 1 is y minus 1. Look at this one. I told you the graphs of implicit relationships, or better than the graph of explicit relationships. This red thing is an actual graph, and the squares are made up of infinitely many of these sort of circly ellipse type things. They get closer and closer and closer together like this, and then there's infinitely many of them in there and there and there. This is a brilliant graph, you've got to admit it. I wonder if I can differentiate its function. I wonder if you can differentiate its function. It's pretty hard, this one. Let's have a go. Right, e to the no. So our mother function is e. So the derivative of e is e, that's easy. So that's that bit done. Now we need to multiply by the derivative of the baby. The baby in this case is sine x plus cos y. We're differentiating with respect to x. The derivative of sine x is cos x. And the derivative of the derivative of cos x is minus sine x, but this isn't cos x, it's cos y. So this is a mother function in itself. The derivative of the mother function cos is sine, so that's sine y, but then we have to multiply by the derivative of the baby, and I'm going to write it like this, the baby is a y, because I don't want it to look like it's sine y dy by dx. It's not that, it's sine y times dy by dx. So I'm going to put those brackets in just to make that clear. Okay, so that's that side done, and the other side is sine of e to the x plus y. So the mother function here is sine. Here we go, differentiating sine. Let's just leave that baby alone. There's the little baby inside still. And now we multiply by the derivative of the baby. Now the baby is e to the x plus y, so it's another mother function inside a mother function. So now we are, let's make it a bit smaller so I don't have to go down a line. Now we are multiplying by the derivative of the baby. The baby is e to the x plus y. Turns out the baby is a mother, so we've got to multiply by this. So the mother function is e, so that's e to the x plus y. But now we have to multiply by the derivative of the baby. The baby is now x plus y. Derivative of x, 1. Derivative of y, dy by dx. And that beautiful thing there, well, it isn't the derivative because I haven't rearranged it to say dy by dx equals, but it is a function which I could put x and y into and get dy by dx, which is pretty cool. Look at this graph. This is a good graph. Sine x squared plus y squared equals cos xy. It's not even that complicated. So let's see if we can differentiate this implicit function. Okay, outside mother function is sine, derivative is cos. Baby stays inside. Then multiply by derivative of baby. Baby is x squared plus y squared. Derivative of x squared 2. Derivative of y squared is a mother function with the mother function being squared, so we get 2y. The baby is y, so we multiply by the derivative of the baby. Equals cos xy, mother function cos, derivative minus sine, baby inside. Now we multiply by the derivative of the baby. The baby is a product. Hold the x still, differentiate the y. Hold the y still, differentiate the x. Derivative of x is just 1. There we go. Did you get that right? If you did, you can be very proud of yourself. Now this is one of the coolest graphs ever. This is genuinely the equation of that graph. That is brilliant. So let's see if we can find the gradient function so that we can find the equation of the tangent. Right, I'm not really going to do that. Even I'm not going to do that. That looks a bit complicated, doesn't it? It would be massively fun, but I think I've run out of time on this video, unfortunately. If you fancy a challenge, you go right ahead.